Welcome to my YouTube channel. This today's session here today we'll discuss on Bragg's law related few problems. So we discussed in our previous lecture in part 1 of Bragg's law and X-ray diffraction. There we have focused on X-ray, the crystalline lattice, how this X-ray diffraction and Bragg's law is related to each other, how we can find out the displacing wavelength of X-ray, etc. So today we'll just before going to problems, that what is Bragg's law, we already discussed in details this, that in 1912 the Braggs, W.H. Braggs and W.L. Bragg discovered the famous most beautiful the law of X-ray related with the d-spacing and wavelength, that they have mathematically derived a relation that 2d sine theta is equal to n lambda. So where d is the distance between two plane and sine theta is the angle of incident ray with respect to the plane, and n is the different order like 1 2 3, and lambda is the wavelength of X-ray. So let's move on to the first problem. In your previous lecture we discussed two problems, how to find out the phase difference of two planes and how we find out the d. So today will be with different some problems will be discussed in this session. So let's move today's first problem, that is from Bragg's law. It is the third problem, that X-ray wavelength is 1.54 angstrom are incident on a crystal. The first order diffraction occurs at angle theta is equal to 30 degree. Find the interplanar pacing d. This is a very straightforward problem. So to solve any of the numerical problem, the first step is we have to list out that what are the parameters is given here. So the wavelength lambda is given here. So that is basically lambda is equal to 1.54 angstrom. Then it is given the first order diffraction. So you know the first order diffraction, that n value is equal to 1. So first order means n is equal to 1, and the theta is given here, that theta is equal to 30 degree. So we already familiar with the Bragg's formula, that is 2d sine theta is equal to n lambda. So in this case we have to find out d, so we can write the formula as n lambda divided by 2 twice of sine theta. So now let us put all the values here. So it is basically n is 1 into lambda is 1.54, so it is angstrom. So as I mentioned that it is a practice, that a good practice to convert in SI units. So 1.54 we can convert, or even without convert also we can get it, because we will be finding the d only, so it will be again with the unit of angstrom only. So we can, may or may not, we can convert it, divided by twice of sine 30 degree. So if you just quickly calculate this, we can find out that d is equal to 1.54 angstrom. So this is our, it is a very simple and easy problem if we know the Bragg's law with X-ray wavelength and the order of diffraction and incident ray theta value, then one easily can find out the interplanar pacing of the crystals. So now let's move for the fourth problem. So that is given here that a crystal has interplanar pacing of d here is given. So that is basically 2.5 angstrom. X-ray of wavelength 1 angstrom are used. Find the Bragg's angle for first order reflection. So Bragg's angle here it asks. So we know if we rewrite the formula in the form of this sine theta, that is basically n lambda divided by 2d. So first order means it will be 1, then 1 twice of 2.5. So we are finding out that sine theta is equal to 1 by 5. So now if we see that sine theta is here, we are getting that is 1 by 5. So theta will be sine inverse 1 by 5, that means 0.2. So that is nothing but will be equal to theta is equal to, this is theta, theta is equal to 11.5. So now let us see some conceptual questions, that what is the maximum possible order for order of diffraction in Bragg's law. How we can predict it. It is very important and interesting to know that what will be the maximum possible order of diffraction. So the problems is why is there a maximum possible order of diffraction in the Bragg's law. So because here the law is related with the angle of incident ray. So we know that sine theta value is basically less equal to 1. So from our Bragg's law, that is 2d sine theta is equal to n lambda, one can write as this formula, sine theta is n lambda divided by 2d. So if so, then if we have the sine theta is less equal to 1, then we can write here that n lambda less equal to d. So if so, then we can maximum order that will be n max is equal to 2d divided by lambda. So this is the possible maximum order can be find out from the Bragg's law. So with this we can also find out the d value, and then we can go one more, that we know the interplanar placing d related with the lattice parameter. So and then we can find out that HKL values relations with the HKL values, also Miller indices that we have discussed in our earlier lecture. Now we'll be just summarize the application of X-ray diffraction. So it basically uses the determination of crystal structure first, and then is the phase identification. So it can be study of various materials including alloy and composite. Once you know the phase identification and the structure, then we can also find out the trace and the strain determination that could be find out. And another important parameter of the crystalline materials which need to estimate and understand that determination of the crystalline size. Why size is important? Because the crystalline size depends based on the crystalline size, the material properties, their optical properties, electrical properties, mechanical properties is important, which is very important to know before using the crystalline material, in particular the semiconductor material, for their applications. And next is the determination of orientation of the single crystals. When we discuss about the crystals, we have find out the crystals have periodic arrangement, have the random arrangement. Based on that, crystals we have classified as different way. So the based on the orientation, the disk spacing value will be changed. Once the disk spacing value is different, then again it is related in the lattice parameters. So it is one of the crucial parameters again in the phase. Since one to another is the interrelated, so determination of uh, orientation of single crystal is important, and another is the determination of the structure of polygrained material. We know the polygrain material are solid material composed of many small crystals called as grain, and each having own crystallographic orientation. So these grains are separated by grain boundaries. So it is also for a polygrain material, the determination of the structure means their orientation of the planes is important to know. So this type of structure, basically the each grain is a single crystals. Grain orientations are random, and grain boundaries are irregular region through grain, and also the size of the grain can range from nanometer to millimeter. So there are many examples like mostly metals like iron, copper, aluminium, ceramics, polycrystallines, silicon generally used in the solar cell, many thin films and engineering alloys. So these are the is quite different from the other materials that they are continuous crystal lattice, and they having the many small crystals or grain, they having the grain boundaries, and this is also once again it's very important for their mechanical, electrical and thermal properties tuning. So in this lecture is today is up to this. Thank you for watching my video. If you like my video, please click the like button. Thank you very much. We will be come back with another lectures. Stay tuned. Thank you.